This is going to be the lecture over section 15.7. This will be the final section for chapter 15. The internal energy of an ideal gas depends only on its temperature, not on its pressure or volume. Now, for non-ideal gases and for solids and liquids, the internal energy generally depends on both pressure and temperature. So the molar heat capacities C sub V and C sub P of an ideal gas are going to be related as follows. And then you can see the equation right here. The ratio of the molar heat capacity at a constant pressure to the one at constant volume is going to be denoted by gamma. And so gamma is going to be the relation of C sub P divided by C sub V. For an adiabatic process taking place in an ideal gas, the quantity T times V to the gamma minus 1 and P times volume to the gamma are going to be constant. You can see the adiabatic process here as it goes from A to B, and an adiabatic curve at any point is always going to be steeper than the isotherm passing through the same point. The temperature of this isotherm is going to be here. This one's going to be a little bit greater. So you're falling from a greater temperature to a smaller temperature. Since it's adiabatic, there is no heat being added in, and then the change in the internal energy is going to be minus the work. So, gone through most of this already. If you take a free expansion and you take a thermally insulated container with rigid walls and divide it into two compartments with a partition, and then when the partition is removed, the gas expands to fill both parts of the container. This is called a free expansion. The gas does no work because the walls of the container don't move. So both Q and W are equal to 0, so the internal energy is going to be constant. And it doesn't matter if it's an ideal gas or not, that's just how it's going to be. Does the temperature change during free expansion? If it does, then the internal energy stays the same. In that case, the internal energy must depend on both temperature and volume, or both temperature and pressure, but certainly not on temperature alone. But if the T is the same after the free expansion, a process for which we know this is constant, then it must be the case that it depends only on T and not on those two. So the conclusion is that the internal energy of an ideal gas depends only on its temperature, not on the pressure or the volume. So if we've got a constant volume temperature change, the system does no work, and the change in the internal energy is going to be equal to the heat that's added, Q. In a constant pressure temperature change, by contrast, the volume must increase. Otherwise, the pressure would not remain constant. As the pressure expands, it does an amount of work W, and according to the first law, we've got this. So for a given temperature change, the heat input for a constant pressure process must be greater than for the constant volume process because additional energy is needed to account for the work done. So C sub P is going to be greater than C sub V. And you can see this is going to be the same description as what we'd had before. If you've got constant volume, then you would go from here to here. There is no work done. If you go a constant pressure here, then the gas has to do work. Remember, you've got space under here. You've got the volume or the pressure here and difference in volume. You've got work going on. This is, again, going to be the relationship between the two. So for an adiabatic process, it's going to be a process in which no heat is transferred between the system and its surroundings. Q is going to be equal to 0, and therefore the change in internal energy is going to be minus the work. Zero heat transfer is an idealization, but a process is approximately adiabatic if the system is well insulated or if the process takes place so quickly there's not enough time for any heat to flow. An adiabatic process for an ideal gas is going to be shown here. That's the same figure as what we saw before. The volume expands from A to B. Temperature drops because it does positive work. decreasing the internal energy. So if point A, representing the initial state, lies on an isotherm at T plus delta T, then this ends up at just T. If you were to take this and compress it back, you would notice that the temperature would rise. The air in the output pipes for air compressors used in gasoline stations and paint spraying equipment and to fill scuba tanks is always warmer than the air entering the compressor because of the approximate adiabatic compression. When air is compressed in the cylinders of a diesel engine during the compression stroke, it gets so hot that fuel injected into the cylinders ignites spontaneously. So again, we've got our relationship here. And for an isothermal process, the product is going to be constant. So P is inversely proportional to V. Turns out for an adiabatic process, this product is constant and P is proportional to this. So when V increases, the pressure decreases more rapidly than for an isothermal process. That is going to be the discussion over chapter 15.